sklearnpreprocessingQuantileTransformer. Description: the quantile transformer is a feature transformation technique that maps the features to a uniform or Gaussian distribution. It essentially converts the original distribution of each feature to a new distribution, which is either uniform or Gaussian, regardless of the original distribution. It achieves this by mapping the percentiles of the original data to the percentiles of the target distribution. Inputs: X. This is the input data, represented as a two-dimensional array matrix where each row corresponds to a sample and each column represents a feature. Output distribution: this parameter specifies the target distribution for the transformed features. It can be set to uniform for a uniform distribution or normal for a Gaussian distribution. Outputs: transformed X. The transformed feature matrix, where each feature has the specified output distribution. Steps: calculate the quantiles for the input data. The quantile transformer first computes the quantiles for each feature in the input data. Map quantiles to target distribution. The calculated quantiles are then mapped to the quantiles of the target distribution, either uniform or Gaussian. Transform the input data based on the mapped quantiles. The original data points are transformed to the desired distribution. Metrics: quantile scores. The quantile scores after the transformation can be used to assess how well the desired distribution is achieved. Distribution plots: visualizing the distributions of the features before and after the transformation can provide insights into the effectiveness of the quantile transformer. Visualization plots: histogram plots comparing the histograms of the features before and after transformation can illustrate the change in distribution. Probability density plots: plotting the probability density functions of the features before and after transformation can further highlight the transformation's impact. Fine-tune parameters: output distribution uniform, default, or normal. This determines the target distribution for the transformed features. N quantiles: this parameter specifies the number of quantiles to use when computing the quantile transformation. A higher value of n quantiles results in a more precise transformation, but might lead to longer computation time. Random state: this parameter allows you to control the randomness in the transformation, which can be useful for reproducibility. Uncertainty methods: bootstrapping: this method involves resampling the data with replacement and performing a quantile transformer on each bootstrap sample. The resulting transformed features can then be used to estimate the uncertainty in a transformation. Challenges and fixes. Challenge 1: handling outliers. Outliers can have a significant impact on the quantile transformation, potentially distorting the target distribution. Sample use case that resulted in challenge 1: when dealing with a data set containing a few extreme values, the quantile transformation might shift the majority of the data towards the extremes, resulting in a distorted distribution. Fixes to challenge 1: preprocessing. Implement outlier detection and removal techniques before applying a quantile transformer. Capping: limit the extreme values to a certain range to reduce their influence. Robust quantile estimation. Use robust quantile estimation techniques that are less sensitive to outliers. Challenge 2: memory consumption. The quantile transformer can require significant memory, especially when dealing with large datasets. Sample use case that resulted in challenge 2: when working with a dataset with millions of samples and thousands of features, the memory required to store the quantiles and perform the transformation might become excessive. Fixes to challenge 2: chunking. Process the data in smaller chunks to reduce memory usage. Sparse data representation. If the data is sparse, Consider using sparse data structures to reduce memory consumption. Memory optimization. Implement memory optimization techniques to reduce the memory footprint of the algorithm.